So right now we're going to look at a reaction that's very similar to the aldol reaction and aldol condensation reaction. There's something called the Claisen condensation. Condensation because you're spitting out a small molecule. Just so you guys know, condensation doesn't always mean spitting out water. It just means spitting out something small. Alright? So the main difference between the Claisen and aldol condensations is the fact that in the aldol reaction and aldol condensation, you start off with an aldehyde or a ketone. Claisen is exactly the same thing, except you start off with esters. Otherwise, the mechanistic aspects of the reaction are virtually identical. All right. So what you have is either one ester or two different esters, one of which has alpha hydrogens, and they react in the way you've seen before. We'll go through the mechanism anyway. But if we look at a reaction like this, we have these two esters, we have some ethoxide base, we have a second acid step which we haven't seen before, but we'll see why that is. And we form something called a beta keto ester. In other words, the ketone that you end up with is beta to the ester group. All right, hence the name beta keto ester. So let's have a look at the mechanism and see if we can figure out what is happening. Well, hopefully you can see from these two esters, only one of them actually has any alpha hydrogens. The alpha carbon on this benzene ring here already has 4 bonds to itself, so that can't have alpha hydrogens. So all we're going to do is form an enolate the way we have done before. Alright, so here's our ethoxide, and you know what this is going to do. It's going to do exactly what a base does in the presence of a carbonyl group like this with alpha hydrogens. Alright, these are all equilibrium steps. So here is our enolate. And once again, this is exactly what you guys have seen before. The only difference is the enolate in this case is of an ester rather than an aldehyde or a ketone. Alright. So there's our enolate. As always, the enolate exists in 2 resonance forms, with the electrons on the oxygen or with the electrons on the carbon. We're just going to keep this right here. Now, let's see if we can figure out what's going to happen when these two react. All right. Well, our enolate electrons are going to do exactly what they always have done before. The electrons from the O- go back down, kick out the double bond electrons, meaning this carbon, if we call this carbon 1, 2, 3, and 4 here, meaning carbon 2 is the nucleophilic carbon, and that goes up and attacks the carbonyl group from the other molecule, in this case the other ester. So let's draw those arrows going up here. And when those electrons hit this carbon, exactly the same thing happens that always has happened when a nucleophile attacks the carbonyl group, and that is that the electrons go up onto the oxygen. Alright? And I'm going to call this carbon A. Alright. Once again, we want to be careful about drawing out our product. Let's do a couple of equilibrium arrows there. We're going to have to go on to a second page here, but let's see if we can draw out the product. So we're going to start off with our reformed carbonyl here. We have our OCH3. Alright, we have our carbonyl group that we've just reformed. I'm going to draw on the 4 carbons that we already indicated. So we've got carbons 1, well, that should be a 1, 2, 3, and 4. Alright. Now, if I was to ask you guys then, which of my 4 carbons is the one that became bound to carbon A, you would of course say carbon 5. Well, no, of course you'd say carbon 2. Alright, carbon 2 is the nucleophilic carbon. So we know we've actually then formed a bond between carbon 2 and what other carbon? Carbon A, that's right. And what's bound to carbon A? Well, we have an O-, we have another OCH3, and we have our phenyl group. All right, so let's put all those on there. Now, what do you think is going to happen at this point? What is that O minus going to do? And bear in mind, we have not thrown the H3O plus in yet. This is still all the result of the base and the enolate attacking the other carbonyl. Well, if you've ever seen anything like this before, you've seen these electrons go back into here, and do we have anything that could come off in this molecule, specifically at this carbon? Do we have a leaving group? Well, the answer is, of course, we do have a leaving group, and it's the OCH3 here. So those electrons could come off like so. We've seen this step before. Now, let's see, can we draw out what we would get here? We have carbons 4, 3, 2, and 1 here that essentially have remained unchanged. We have our OCH3, here's our carbonyl. Alright, now, let's see if we can draw out what we have here. So we have that, we have our phenyl group, and actually at this point it looks like we have our product, because if you compare this to what we have here, it looks to me like those are pretty much exactly the same thing. And, well, the fact is they are exactly the same thing. So that might make you wonder, well, if we've gone from here to here, we haven't used H3O plus yet. What the hell is going on? Is this some weird new funky chemistry that Dr. P hasn't told us about? Well, no, it's not. Bear in mind what we have generated here. We generated OCH3 minus, or CH3O minus, however you want to draw it. But take a look at this molecule. All right. There is something special on carbon number 2. Anybody know what is on carbon number 2 that is going to give us some issues? Well, look at what we have on 2. We have an alpha group, we have a couple of carbonyls. What else do we have on carbon number 2 there that we haven't shown right now? Well, what we have is a hydrogen. Is there anything special about that hydrogen? Well, if you said it's an alpha hydrogen, you'd be right. But it's not just any old alpha hydrogen. This is a super acidic alpha hydrogen. Anybody have any ideas why it's super acidic? Well, it's super acidic because it's in between 2 carbonyls, and we've seen already that alpha hydrogens in between 2 carbonyls are much more acidic than alpha hydrogens that are not. So the question then results is, well, what's going to happen between this and this? Because this is a strong base that we've just generated. What do you guys think is going to happen? Well, not surprisingly, this strong base is going to grab that really acidic hydrogen. And let's just put those electrons up onto that carbon. Now, I don't normally like to do this, but I'm going to have to move on to a next page to come up with the enolate of what we generate here. So we're going to have the same structure, except we're going to have generated our enolate carbon. Now, look at the way I drew my arrows here. I'm going to have the electrons up onto the carbon. I could have equally well drawn the electrons up onto the oxygen here. It doesn't really matter. So let me just draw out what we have here. Just talk amongst yourselves whilst I'm drawing these structures out. Okay, I'll get there in just a minute, or at least I hope I will. So when I draw out that, and I have this, there's my electron pair, and there is my negative charge. That's my enolate. Now, just to make sure everybody is clear about this, the enolate exists in 2 forms, and we've already seen this. Just so you guys don't think I'm doing something different in the 2 enolates that I formed, when I draw out the other resonance structure here, you'll see something that looks very similar to the other enolate that we just generated. Alright, where I have the double bond between the 2 carbons, and the negative charge on the oxygen. Please, please, please make sure you understand that both of these are resonance structures of the same thing. All right? Remember, we hadn't added in our acid yet. And this is where our acid actually comes into play. Because we have an enolate, but that now has nothing to react with. And unless we give it something to react with, it's going to start doing all sorts of funky things that we don't want it to do. Because enolates are pretty reactive. So what we do is, we say, here's some acid. All right? Protonate yourself and make yourself bloody happy and go away. All right? So that begs the question then. Which atom, the carbon or the oxygen, is going to be more nucleophilic? Or more basic, I should say. Is it going to be the carbon or is it going to be the oxygen? Well, we know the carbon's more nucleophilic. So that would suggest then that the carbon is also more basic. Now, exactly how you push your arrows at this point depends on which resonance structure you were starting from. Okay. If we were to start from this resonance structure, let me just, oh crap, what have I done? Let me just erase these two red arrows here if I can without balls and everything else up. Crap, I can't, oh well. Oh, shit. Oh, sorry, I didn't say shit, although I just did. There's our negative charge. If we were to show the reaction from here with the acid, we could just show that attacking the hydrogen. Oops. That's a rogue red mark there. That shouldn't be there. Please believe me. And then all we would get would be the same product that we had before. Alright, so if I draw this out again, we have our OCH3, we have the ketone, and we have the phenyl group. And we also form some water. Alright. Now, you might be wondering then, well, if this acidic hydrogen was removed before, why can't it be removed again? Well, what we had before was CH3O-, and that bound with the hydrogen to make the CH3OH that comes off at the end. So therefore, all we have here is water and CH3OH, which are nowhere near strong enough nucleophiles to remove that hydrogen. So at this point, that means this is our product, and the reaction is over. So if I was to ask you for a mechanism for this reaction, it would mean all the stuff on the first page and on the second page too. Now let me just do one more thing before we finish. I showed the reaction between the negative carbon and the acid. If, however, you were starting from this resonance structure, you kick your electrons back down to your carbonyl, kick the electrons from the double bond out, and those would attack the hydrogen. Either way, you would get the same result. Okay, so it doesn't matter which of these two resonance structures you use. Some people prefer to do this one, some people prefer to do the other one. Frankly, it doesn't matter which one you do. The overall result is that in a Claisen condensation with these two steps, you start off from two ketones, preferably one with alpha hydrogens or one without alpha hydrogens, or two of the same, sorry, I should have said two esters, one with an alpha hydrogen, one without, or two of the same ester. Addition of those two with these reagents gives the beta keto ester, and if we just check that for sure, we'll see here's the ester, alpha carbon, beta carbon, we have made a beta keto ester, and that is the Claisen condensation.